Yeah, we can hear you.
Great. Yay. I think it's all there. Okay, folks. So today we're going to do spin orbit coupling. That's the plan. So let's get going. So the idea is that what we're doing is we're figuring out what we call the hydrogen fine structure. And what that means is that we're starting with a hydrogen atom. That's the nucleus, and that's the 1/r potential, and these are the energy levels. N equals 1, N equals 2, N equals 3, etc. And we have we know that for hydrogen, we have our favorite basis N, L, M sub L, M sub S, and we know that that equals E sub N psi naught N sub L, N L M sub L, M sub S, where En naught is negative 13.6 eV over N squared. Okay, so that's hydrogen, and you guys all did that last semester, and so you kind of hopefully remember what all these things are. You know that psi N sub L, M sub L, M sub S, we can write that as a radial part M sub L, N L, times a angular part, and L, angular part is L M sub L, and the spin part is S M sub L. Okay, so this is just sort of review. And so what we're doing is we're now adding perturbations so that now the new hydrogen, I'm sorry, the new Hamiltonian is equal to the original Hamiltonian plus some perturbation. And then we're looking to see what is the change in energy for all the eigenstates. Okay, so what is the change in energy due to the perturbation? Okay, that is what the hydrogen fine structure is these changes of energy due to these various perturbations. And so last time we did the relativistic perturbation. We did H prime relativistic. And this time we're going to do the spin orbit. Spin orbit. And so what we have to do then, so the first thing, the starting point is always figuring out the Hamiltonian. What is the Hamiltonian? And the Hamiltonian is always classical. So remember, classical physics is part of quantum mechanics. The Hamiltonian is always a classical object. It starts as a classical object, then we convert it into an operator, and then we solve the Schrodinger equation. But we always have to start with the classical Hamiltonian. It always starts with classical physics. That's something that's easy to forget. So basically, is that the idea is that last semester when you did the hydrogen atom, you forgot something in your classical mechanics. You just did the Coulomb. Last semester when you did the hydrogen atom, you did the the electron circling the proton, and it has some spin S, and you forgot something. And what you forgot is that it's sort of not completely obvious, but what you forgot is that I'll give you a simple intuition for what you forgot. What we forgot to do last semester is that a charge moving, I'll just use the word charge. When I have a charge move in an E field, then the charge experiences a magnetic field. And that's maybe not obvious. That's really a relativistic effect. And so maybe some of you have seen this and some of you have not. It's a relativistic effect that, you know, it's the kind of thing that was supposed to be covered in physics 7C when you guys learned relativity, but maybe fell through the cracks. I don't know. But this is a result from relativity. So it's a classical physics result from relativity. And then if the charge feels a B, then if the charge has spin, then the charge has a mu, and then there's an energy, negative mu dot B. All right, because if I have a magnetic moment in a magnetic field, then there's an energy, and that's the energy that you forgot. That's the missing part. And that's the spin orbit coupling. Okay, so that's the intuitive part. But now let's derive it in more detail. But I want to try to give you the intuitive feeling. So that's a classical effect that you guys neglected last semester, and now it's coming back to bite you. And it's actually very important. And so let's derive this in sort of more detail. But I want you to just to understand that it's coupling it's basically coupling the motion of the electron with the spin of the electron, because this B field comes from the motion and this mu comes from the spin. So when people say spin orbit, it's really coupling the movement of the electron with the spin of the electron to create a new term in the Hamiltonian. That's very important. Comes up all the time. Okay, so there's different ways to derive it. I'll show you my personal favorite. My favorite derivation, and there's different derivations for it, but I'll show you my favorite one. My favorite derivation is as follows. Let's do this. Let's consider, this is the situation. We have a proton and it has an electric field that's sticking out, E, and we have the electron that's moving in it. And the electron has a spin, S, and it's moving in that electric field with some velocity, V. And so the thing that you're supposed to remember, but probably none of you do remember, maybe one or two of you do, I don't know. It's not like a formula that everybody remembers, but what you're supposed to remember is that for a charged particle moving in a B field, then so charge moving, a charge moving in an E field feels an effective B field. B is equal to minus gamma over C squared V cross E in the rest frame of the charge. Okay, and where gamma is your famous relativistic factor, that you all learned at some point, 1 over square root of 1 minus v squared over c squared. Okay, so this is the relativistic effect, and this is the starting point, relativistic. And so that means that this electron spinning around the nucleus, it's moving, it has a velocity and an E field, so it feels a B field. Let's first assume that the velocity is not so big. That the velocity divided by c is small, in which case we can make the assumption that gamma is approximately 1, and so then we then have that the B field experienced by the electron is equal to negative v over c squared cross E. Okay, so that's just coming from that starting formula. And so then we do let's do some little tricks. Let's multiply. The first little trick we'll do is let's multiply times m over m. And so then when we do that, the m times v on the top turns into a p. So then we get minus p over mc squared cross E is the effective B field. And now let's flip the order, in which case, because it's a cross product, then there's a negative sign. So this then is equal to 1 over mc squared E cross P. Okay, so that's the B field experienced by the electron. So remember what we're even talking about. And so then we have a little, now we have this is felt by the electron, but we have to remember that the electron has a magnetic moment. And remember that a particle with spin, the magnetic moment of any charged particle with spin is equal to G times Q divided by 2 times the mass of the particle times the spin of the particle. And for an electron, what is G? Someone tell me. What is G? The gyromagnetic ratio, it's a famous number for an electron. This is the formula. Yeah. This is a formula for any charged particle. But now let's, like it works for the proton. What's the G factor for the proton? Does anybody know?
Professor, where are we supposed to have studied the gyromagnetic ratio?
I don't know. Because the thing is, it's like these are things that you learn in different, the problem is that people learn these things in different, in different classes. Like, for example, a lot of people learn this in 137A, because if you're doing, for example, the Stern-Gerlach experiment, when you learn spin and the electron goes flying through the Stern-Gerlach and it separates into spin up and spin down. Well, the only way to understand that is through this interaction. So a lot of people will learn this in 137A, but it's normal for things to fall through the cracks, so don't feel bad. Just be glad that you're learning it at all. So the gyromagnetic ratio for an electron is 2. For a proton, it's 5.6, and we'll use that later. So any charged particle has this magnetic moment, and so that means for an electron, Q is minus E, so it's minus E over M times S for electron. Okay, so that's the magnetic moment of an electron. And so that means then that the energy, the energy felt by the electron when it's moving to the electric field is going to be negative mu dot B. And that's something that I know you all know, because that's just the energy of a magnetic dipole in a magnetic field. And that's something that you learn in, I forget, physics 7B or 7A or something. So that's the energy of a magnetic dipole. All right. And so that means then, let's just plug it in. So then that means that our Hamiltonian, H, and I'll use this terminology now, I'll use H prime. That means that this new energy term is equal to, let's just plug it all in. So negative mu is going to be negative times negative E over M S, that's the mu, dot B. And the B is that weird formula we just derived, which is 1 over mc squared E cross P. All right, and this is all actually classical, except that magnetic moment of the spin. That's really a quantum mechanics result, but that's just a formula that we learned. That really comes from the Dirac equation. We're not deriving that. This expression, the magnetic moment of a charged particle spin. That's not something we can derive in undergraduate quantum mechanics. That comes from the Dirac equation. I actually will derive it at the end of the course. The last 2 lectures, I actually will derive that, but not now. Okay, so let's keep going. And so now let's just do a little trick. Let's plug in the expression for E. Plug in for E. And so E is equal to, actually, can anyone tell me what E is? The electric field, the little formula for the electric field, does anybody know it? What is the expression for E? Well, maybe I'll make the question simpler. Where is E? What's creating the electric field? What is creating the electric field that the electron experiences?
Proton.
Say it again.
The proton.
Yeah, exactly. So we just need to know the proton is a point charge. We think of it as a point charge, so we just need to know the electric field of a point charge. And you guys all know that from some class that you took. I forget which one, but you've all seen it. And so this is the electric field. It's E, the charge of the proton is E. That's why it's plus 4 pi epsilon naught r squared times r hat. Okay, because it's a unit. The direction is out. I mean, here it is. I've drawn it up there. So here it is. I'll just say E over 4 pi epsilon naught r hat over r squared. So that's a formula you've all seen somewhere. And so let's just use that formula. But let's rewrite the formula. Let's remember that r hat is equal to r vector divided by r. So that means that this formula can also be written as E over 4 pi epsilon naught r cubed times r vector. Okay, it's convenient for me to write it like that. So now we're going to plug that in here. And so now we see that H prime is equal to E over M S dot, oh man, lots of constants here. Do I have to write them all? Let's see. I'm going to sort of combine a few constants just to save some writing. So it's going to be E squared over 4 pi epsilon naught times 1 over M squared C squared R cubed times S dot R cross P. Okay, so a little bit of math, but nothing too hard. And so now let's notice that this thing is, what is that equal to? Somebody tell me.
Angular momentum.
Yeah, that's equal to the angular momentum of the electron, That's right, L. Also, we have to multiply times a factor of 1/2, which comes from, this is a tricky thing. We call this the Thomas precession. Term, due to the fact that electron is in an accelerating frame. X. So this is like a little detail that we skipped. Because the relativistic formula that I used for the magnetic field was for an inertial frame. And we're actually in an accelerating frame. So that's where that factor of 1/2 comes from. But that's just a little that's just a detail. We don't need to get too caught up on that. And so then we have this. We have that the H prime is equal to, I'll call it, now I'm going to call it what everyone calls it. We call it the spin orbit term. The spin orbit Hamiltonian is equal to E squared over 8 pi epsilon naught times 1 over m squared c squared r cubed times L dot S. And the reason I can move, I have to remember that L and S. Well, I'll ask you, do L and S commute? Yes or no? Orbital angular momentum and spin angular momentum, do they commute?
Yes.
Good, they do, because they're acting on totally different dimensions. One operator is acting on spin, the other is acting on space, so they totally commute. So that's why I can write it as S dot L or L dot S. I can just freely change the order because they commute. Okay, and so when you look at this formula, a way to think about it in your head is like the L, you can think of the L, the angular momentum, as creating an effective magnetic field. And the spin is experiencing that magnetic field. So it's like, and so the energy in a magnetic field is, mu dot B or negative mu dot B. And so here the mu is coming from the S and the B is coming from the L. So that's how you intuitively remember this formula. And it's a real thing. So L dot S is the energy of the electron in the E field. And the reason why I like this derivation that I just gave you is because it's a very general derivation, because I use this derivation to derive what happens when the electron's going around a proton. But there are other situations where electrons are just moving through some other electric field. They could be at the surface of a crystal, or in an electrical device, in a computer chip. And just anytime an electron is moving through an electric field, this Hamiltonian will play a role, the L dot S. So it's a very general effect, even more general than it looks today. Okay, so now what we do is we ask ourselves, okay, what are the changes in the energy levels of the hydrogen energy levels? How does the hydrogen energy levels change? How do hydrogen energy levels change due to the spin orbit? And so that's what we got to figure out. What we got, okay, so what are we going to do? How are we going to figure that out? What are we going to use? Somebody tell me. What technique will we use to figure out the change in the energy levels of a hydrogen atom due to this new term in the Hamiltonian?
Perturbation theory?
Yay, that's right. Because we're going to use perturbation theory, PERT theory. Because we're going to have H equals H naught plus H prime, where H prime is the spin orbit term. Okay, the spin orbit coupling. So, okay, so let's do it. So then what we have is, so we have to, so for perturbation theory, the first thing you do is, well, you have to pick your basis. And so let's pick our favorite basis. This is our basis, the N, L, M sub L, M sub S basis. And so let's remind ourselves, you know, this is the hydrogen atom, and we have the N equals 1, N equals 2, N equals 3, etc. And so that's our basis, where these are the eigenstates. And so then the question is, the first thing we have to ask after we know our basis is it degenerate? Yes or no? Is our basis? Yeah.
Yes.
Yeah. Massively degenerate. It's degenerate by 2n squared, right? Each level is 2n squared degenerate. So we have massive degeneracy in the hydrogen atom. And so then the next question we have to ask ourselves is what? In order to apply the formulas, our lovely little perturbation theory formulas, we have to ask a second question. What is that? What is it? Someone tell me.
Are the matrix elements 0?
Exactly. Are the matrix elements H, I'll call it these, H prime, I'll do it like this, M, N equal to 0. But what are these matrix elements? Which ones are we talking about? Someone tell me. Which matrix elements?
The non-diagonal ones?
Right, the non-diagonal ones, but you're, yes, so these are the off-diagonal matrix elements. That's correct, but it still doesn't tell the whole story. Which off-diagonal matrix elements?
In degenerate subspace?
Exactly. In the degenerate subspace. That's exactly right. So we only care about the off-diagonal matrix elements in the degenerate subspace. And so here, like for example, let's look at n equals 1, then we have L equals 0, and so there's only one state where I have M sub L equals 0. So there's no degenerate subspace for n equals 1, but for n equals 2, I have L equals 1, which then has 3 states, M sub L equals 1, 0, minus 1. And I also have L equals 0, which has 1 state, M sub L equals 0. And so this is a degenerate subspace. Degenerate subspace is that set of states. All of these states form a degenerate subspace, right? And for L equals 3, I have L equals 2, which has 5 M sub L states. And I have L equals 1, which has 3 M sub L states associated with it. And then I have L equals 0, which has just 1. Do you see how I'm writing that? So these states are the M sub L. It's going to be 2, 1, 0, minus 1, minus 2, 1, 0, minus 1, 0. These are the M sub L states. So all of these states at one n level form a degenerate subspace. So those are the states we got to worry about. So we have to ask ourselves, does H prime couple those states? Because for an operator to couple two states means that the matrix element of that operator between the two states is non-zero. That's what coupling means. When people use that, people always use that word, and that's what it means. So we have to ask ourselves, do the off-diagonal matrix elements within the degenerate subspace, is it zero? So okay, so we have to answer this question. So it's not a completely easy question to answer, but let's answer it. And there's different ways of answering it. So there's the brute force way. Let's use the brute force way. There's also an elegant technique that we will learn today. But before we do the elegant technique, let's use the brute force technique to answer this question. So for the brute force technique, you construct the off-diagonal matrix element and you evaluate it. You just go through it and do it. So construct the off-diagonal matrix element in the degenerate subspace. Matrix element, and then evaluate it. Evaluate it. That's the brute force way. I like the brute force way. I told you before I like brute force because it's simple to understand, but it's quite tedious. Okay, so let's do it. And so we have let's write our perturbation. It's a function of R. Where did I put our perturbation? Here it is. There's H prime. So this prefactor is a function of R. So we have so I'll just write as a function of R so I have less writing to do. But we have the Hamiltonian is a function of R times L dot S. And I'll just remind you what f of R is. F of R is E squared over 8 pi epsilon naught times 1 over M squared C cubed. Oh shoot, M squared C squared. Getting these all mixed up. R cubed. Okay, that's f of R. And so now let's construct the off-diagonal matrix element. And so so this is a matrix element, something on the left, H prime, something on the right. Okay, that's the matrix element. And so on the left, let's put an arbitrary state in the degenerate subspace, which is R, N, L, L, M sub L, S, M sub S. That's our eigenstate. And then here's our Hamiltonian, F of R, L dot S, that's the H prime. And now on the right-hand side, we have to write an arbitrary second state in the degenerate subspace. And so I will ask you, then here's the state, the other state. And so does this state have the same n as this state? Is the n the same, yes or no?
Yes.
Good, because that's exactly right, because that's what makes it a degenerate state. It has the same n, good. Does it have the same L?
No.
Yeah, exactly. In principle, it does not, because that's what changes in the degenerate subspace is the L and the M sub L and the M sub S. That's right. So the L can be different. I'll call it L prime. And so now I have the angular part. And so L prime. And how about the M sub L? Is it the same M sub L as on the left?
No,
What?
probably no.
Exactly. It doesn't have to be the same. Now the S, of course, is the same because the spin of a particle doesn't change. That's the one thing that doesn't change. It's S, but the M sub S can change. that's why often we just don't write the S, because the S is like the most boring one, because if I'm talking about an electron, every state of an electron has the same spin, because that's a property of the electron that does not change. So sometimes we just don't write the S, but it's the M sub S that's important. Okay, that's my matrix element. Very good, that's it. Okay, so now let's notice that the radio part does not, I have this acts on the angular variables, and this acts on the spin, but this is the radial function. So he slides right through. So I can rewrite this like this, R and L, F of R and L prime. And then, but I still have my L, M sub L, S, M sub S, and I still have my S, M sub S prime, L prime, M sub L prime. That wasn't so good. Okay, but then what goes in the middle here? Okay, well now I have L dot S, and so to evaluate this, I have to expand L dot S. Actually, I have to evaluate it, and so L dot S is going to be the dot product Lx, Sx, Ly, Sy, Lz, Sz. All right, so that goes inside there. I guess I didn't give myself the right amount of space. And then what we're going to do is these guys are going to hit these guys, right? So these states, when they hit these operators, well, let me ask you a question. Is this state an eigenstate of, is it an eigenstate of Lz and Sz? Is it? Yes or no?
Yes.
Good, it is. And so that means that when Lz and Sz hit it, they're just going to give back numbers. And so this thing can then slide back through, and it's going to hit this guy on the left. What is it going to give me when that thing hits that guy on the left? For this term.
Some factor with an H bar in it or something?
There will be H bars, that's correct. But I want you to just see, I'm sort of doing shorthand, but what I'm doing is I'm breaking it up like this. This term, I just want you to get a sense of what I'm doing. And so then I'm doing this, Lx, Sx, plus, I'm sort of skipping a lot of steps, maybe, you know, but I'm not telling you, sort of assuming, you know, just assuming that you'll see it, but maybe you don't. I just want. Yeah, this is what I'm doing. I'm breaking this up into 3 terms using the associative property or commutative property or one of those math properties that you all have seen before. So we're calculating this term. And so for this term, this thing is going to hit this, and then it's going to hit this. And the point I want to make is that this operator turns into a constant, so I'm going to have this state hitting this state. And what can you tell me about this state on the right when it hits this state on the left? What does that equal?
Will it be some kind of Kronecker delta between the M and the M prime?
Yes,
and the L and the L prime?
that's exactly right. But we can take it a step further, because remember, this is an off-diagonal matrix element. And the definition of off-diagonal means that all the indices cannot be the same by definition. So please take your explanation 1 step further and tell me what it equals.
Are they just zeros?
Yeah, exactly. So the Kronecker delta is 0 because the indices have to be different. And if the indices are different, the states are orthogonal. That's the point I want you to see, okay? So that part just goes to 0. Boom, boom, all right? That just goes to 0. But now let's look at these states, or not states, but these terms. Because now I have Lx and Ly, Sx and Sy. Now, is this state on the right an eigenstate? Now I'll ask you the question, is it an eigenstate of Lx, Sx? Question mark? Yes or no?
Probably not.
That's right, it is not. It is definitely not. And so what that means then is that to evaluate this expression, I have to turn these things into raising and lowering operators. All right. So that means that that means that when this thing in the middle hits these guys, it's going to hit them with raising and lowering operators. And so what that means basically is on the left, if I have on the left, I have N, L, M sub L, and M sub S. And on the right, notice I have N, L prime, M sub L prime, M sub S prime. And so now I will ask you a question. Suppose, what if L prime equals L, and at the same time, M sub L prime is equal to M sub L plus 1 or M sub L minus 1. And at the same time, M sub S prime is equal to M sub S plus or minus 1. What if this happens? That means if this is the case, and then the raising and lowering operator hits it, then the idea is that can turn the right-hand side, which started as a different state. Remember, the right-hand side starts as a different state than the left-hand side because it's off diagonal. But what if those raising and lowering operators hits it and turns it into the same state that is on the left-hand side? Then what happens when they touch? Do they equal 0? Yes or no?
No.
That's right. So the point is you can get a non-zero answer because you started out as orthogonal states, off diagonal, but the raising and lowering operators changed you. So now you're the same. And now when you hit, it's non-zero. So then we can have H prime Mn is not equal 0. Do you see that? And so that is a problem. So this is a big problem. And so what that means is it doesn't work. The scheme, it's the bad scenario that, and the words that we use when this happens, what we say is that you have the words we use, we call it a bad basis. What we say is that psi n l m sub l m sub s is a bad basis. What it means is that if we use this basis, a bad basis basically just means cannot use perturbation theory. Can't use perturbation theory. Because the perturbation expansion blows up. Those denominators go to 0 and you're screwed. It blows up, it diverges. Okay, so what we just determined is that we cannot use our little perturbation formulas to calculate the spin orbit correction, how the spin orbit changes the energy level of hydrogen. Like, oh no, that's terrible. That's a horrid, horrible, horrible thing. And I want you to understand where the problem lies. The problem is here, because this will come back later. We have n equals 1, n equals 2, n equals 3. Let me just look at n equals 3. For the n equals 3 level, we have L equals 2 and all the m sub l's, 5 of them. 2, 1, 0, -1, -2. And we have L equals 1, and then we have 3 of them. 1, 0, -1, and then we have L equals 0, and we have 1 of them. Those are all the states. There's also the S. There are also the S states, but I'm going to ignore those for now. But what I want you to see is that the problem is here. And it's here. I want you to see that it's because the problem occurs when I have the left-hand state is some n sub L, NL, M sub L, M sub S state, and this is the right-hand state in my matrix element. But the problem occurs when L prime equals L for the right state and the left state. When the L's are the same, then the raising and lowering operators can start making them connect. So there's a problem in this. This is my problematical subspace. That's a problem. And this subspace is also a problem separately, because it's this, these are separate little subspaces. This is where the problems occur, because these states can be coupled by the H prime, but it's within where the L is constant. That's going to come back, so that's why I'm pointing it out right now. I want you to see that. Okay, so now how do we fix this problem? So so we need a new basis such that the off-diagonal matrix elements equals 0. Okay, we need to find a new basis. And so there's 2 ways to do this. 2 ways to proceed. The first way is just to brute force diagonalize H prime in the degenerate subspace. And we actually did that in class when I did the covalent bond. When I did the covalent bond example, I actually diagonalized H prime in a degenerate subspace for the simplest case of 2 degenerate states. But now you see that we have this much more complex scenario where now we have 2 n squared degenerate states. So the dimension of our matrix for each state, we're gonna have to do it all over again. So the dimension is, 2n squared for the matrix. 2n squared. I mean, the matrix that we have to diagonalize will be 2n squared by 2n squared. And that's terrible. That's a horrid thing. We don't want to do that. Could you guys please mute yourself? Somebody's making a lot of noise there. I guess there's a way for me to do that. I have to remember how. Participants. Shit. Oh, there it is. Yeah, mute all. Okay, so I just muted you guys, but you could still talk. You just unmute yourself. But then when you're done talking, please mute yourself so there's not lots of extraneous noise. Okay, so all right. So one thing is to do a brute force diagonalization of H prime in the degenerate subspace, but we don't want to do that. We did it before, but now there's another thing, which is we can cleverly find a new basis. Cleverly find a new basis by hook and crook. So what do I mean by hook and crook? Well, the usual thing, hook and crook, means math trick. Let's use a math trick. There's an elegant way to find a new basis. There's an elegant math trick that helps us to, this will help us to find a good basis. What is the definition of a good basis? Somebody remind me. Because we use these terms a lot in perturbation theory. We say, oh, bad basis, good basis. What is a good basis? Somebody tell me. Definition.
One
Is it
with
like
which
a-
you can use perturbation theory.
Yeah, and what is the defining feature of the good basis?
Orthogonality?
Well, all the bases are orthogonal because they're all eigenstates
yeah.
and Hermitian operators. But so that's true. It is orthogonal. You're right. But there's something more. What's the definition of a good basis?
Hamiltonian prime is 0.
Good. Well, I mean, yeah, you're onto it. I mean, the Hamiltonian itself is an operator, so that's not 0. That, you know, that's just the operator. But you're right. Something about that is 0. And what is the thing that is 0 for the good basis? It has to do with H prime.
Inner product of two states.
Yeah, then what's the word we call for that? It's not exactly the inner product. It's close to the inner product. What do we call it? It has a name. It's called a what? I'll give you, it's this thing, right? That's what you said. What is that thing called?
Matrix element?
Yes, I want you to say matrix element. Say it. Every one of you now in your own mind say matrix element. Matrix element. Okay, say it. Okay, so it's a matrix element, but it's not just any matrix element. Which matrix element is it?
Off diagonal.
Yes, and it's not just any off-diagonal matrix element. It's the off-diagonal matrix element in what subspace?
Degenerate.
Exactly. That's a lot of words to say. I'm really sorry. I mean, look how simple it is to write. It's just just H prime Mn equals 0. But to say it, it's like it's the off-diagonal matrix element of the perturbation in the degenerate subspace. Okay. It's in the degenerate subspace. So I want you guys. I know it's a lot of words and it sounds complicated, but it's not complicated. It's, you know, you've got these degenerate subspaces and it's the matrix, and if any of those states are connected through the perturbation, you're screwed. That's a bad basis. But a good basis is one that does not connect those guys. And by what that means then is that H prime is diagonalized in the degenerate subspace for a good basis. All right, that's another way of saying it, because if all the off-diagonal matrix elements are 0, then then you only have diagonal ones, and so that, and if you only have diagonal elements left, then that means you're diagonalized. That's what diagonalized means. It means you're diagonal. Okay, so we got to find a good basis. So how do we do that? So let's use a math trick. And so let me show you the math trick. So we're going to use a very special theorem. Use special theorem, a math theorem. And so let's derive the special theorem. So this is pure linear algebra. So we're just going to do a linear algebra trick theorem. So let's go back to linear algebra. You're in your math class, and the math professor says, suppose that I have two degenerate eigenstates, psi naught A and psi naught b are degenerate eigenstates of some operator. And I'll call that operator for kicks, I'll call it H naught. All right. And then if if they are also non-degenerate eigenstates of another operator, and it's just funny, it's so mathematical, but and if this operator commutes with H prime, then what happens is we have psi naught A H prime psi naught B equals, can you guess? Can anyone guess what goes here? Can you do this theorem in your head and figure it out?
Are we saying that H prime is that T hat?
No, we're not. This theorem, it's actually a really simple theorem, but using it is a little complicated. There's like a few steps of logic. This is actually kind of confusing. It's simple, but confusing because there's not just one step of logic, but two. But first, let's finish the theorem. This is equal to 0. Okay, that's the theorem. This is the magic theorem, and it's pure math, as you can see. But this is the magic theorem that's going to allow us to find a good basis. But let's just, before we figure out all the good basis stuff, let's just understand this theorem, okay? So for this theorem to work, let's just define the theorem. So what we have is, and we're going to prove this theorem too, because it's so important. We're going to actually prove it. It's simple to prove, just a couple lines. But let's set up the theorem, because first, the words that I used mean that this new operator T, well, I'll ask you, does it commute with H naught? Yes or no? And the answer is in that box. Does it commute? Tell me. Does it commute? Yes or no? With H naught?
Oh, it must commute.
Good, exactly. It must. And the trick is to notice that the states are also eigenstates of T. And so to be simultaneous eigenstates means that T and H naught must commute. Okay? So that is part of it. But let's also notice that the fact that psi naught A and psi naught B are degenerate eigenstates of H naught, so means that if H naught hits psi naught A, then it gives me a constant T sub A times psi naught A, where that is the eigenvalue, right? But if H naught hits psi naught B, then it gives me this other eigenvalue, T sub B, psi naught B. And so for these to be non-degenerate eigenstates, what does this tell me about what is the relationship between TA and TB? I'm asking you. Is there any special relationship between TB and TA? Maybe I'll make that a more specific question. Can T be equal to TA? Yes or no?
Well,
What?
oh, I thought because they're degenerate, they might be equal, but that was, yeah, it's because they're degenerate. Shouldn't they be equal? TB and TA?
It's tricky. They're degenerate for H naught. But notice what I wrote. For T, I specifically said that they are non-degenerate. You see it? Read the thing in the box. You see it?
Sorry, Professor, but why do you have H naught as the operator? If
There's two operators. I have two states which are eigenstates both of H naught and of T at the same time. Is that okay? Does that make sense? This is yeah.
I think I'm kind of confused by if TB is not equal to TA, that makes sense if the equations that you wrote there was T, the eigenvalue function of T's. But
Okay, yeah, you're right. I screwed up. Okay, now I can see why you guys are confused. Okay, I'm sorry. Thanks for telling me that. I screwed up. I was looking, hoping I wouldn't screw up, but I did. Oops. Okay, there. Now, hopefully it makes more sense. Okay, sorry about that, guys. Yeah, okay, what is the relationship between TB and TA, the little guys?
they're not equal to each other.
Exactly, they don't equal each other. Yeah, I'm sorry for making that mistake. Okay, good. So, all right. So this is important. And so the connection to quantum mechanics is going to be that, I mean, I think part of the connection is sort of obvious, the psi naught A and psi naught B form a degenerate subspace in H naught. And then we have some H prime which is our perturbation. And so this theorem is telling us that we have to go outside of the problem and find a new operator, T. And then we have to make sure that our degenerate subspace are eigenstates of the new operator. And not just any old eigenstates, but non-degenerate eigenstates of the new operator. And if that's true, then we know that we have a good basis. But if it's not true, we have a bad basis. The converse, it goes both, if it goes in one direction, you have a good basis. In the other direction, if it doesn't work, then you have a bad basis. So let's prove this theorem before we use it. Prove, because it's so important. And it's really, really trivial to prove, actually. So let's do this. Let's prove it. Let's start with the fact that this new outside operator, I'll call it the third operator, because I have H naught, I have H prime, which are your old friends, but now I have this weird T out of nowhere. So this, I'll call them the third operator. So if this T for third, maybe that's why they chose T. Okay, so if you have the T operator, and you guys know that the Hamiltonian, the commutator between T and H prime is 0. That's part of the theorem. And so that means then that if that is true, then if I do a left-hand multiplication by psi A and a right-hand multiplication by psi B of both sides of the equation, then it's still an equation. So let's do it. Psi A naught and you guys have seen these kind of tricks before. Psi B naught equals 0. Okay, so if this is true, then this is true, because I just did the same thing to both sides. But if that's true, then let's write it out. So then that means that 0 is equal to psi A naught TH minus HT psi B naught. Okay. Now that, so now what I can do, let's see, H prime. Okay, but now I have T acting on psi naught A. And what does T then turn into? What does the T operator turn into? Because he's a Hermitian operator, so he can act to the left and to the right. So what does he get when T hits that guy on the left? What does he give you?
TA.
Exactly. But now here he's hitting the guy on the right. What does he give you?
TB.
Yes. And so this thing is equal to now psi A naught TA H prime minus H prime TB psi B naught. Now we just squish it back together again. I skip one step of algebra, but you can see that you get this psi A naught H prime psi B naught times TA minus TB, right? Is that true? And so now what can I say about this thing? Can that ever equal to 0? Can it ever equal 0?
No, because it's non-degenerate in the
Yes, exactly. Does not equal 0. But if this thing times this thing equals 0, and one guy doesn't equal 0, then what does this thing have to equal? What does it equal? Tell me. Say it.
0.
Right. Therefore, psi A naught H prime psi B naught equals 0. And I will just add, and therefore psi A naught and psi B naught are a good basis. So that's the trick. The trick is that we have to find a basis that are non-degenerate eigenstates of a third operator that commutes with our perturbation. So I'll say it explicitly. A good basis is equal to non-degenerate eigenstates of some T, a third operator, such that this third operator commutes with our perturbation. Okay, that is our new definition of a good basis. And I will take it even one step further. I will say a bad basis. And this is sort of, I'm not like doing all the math to make sure that my states are all mathematically, rigorously perfect, but I'm just telling you this is how it works out in the real world. And so there must be some rigorous, you guys could fill in the rigor for me, please. Or tell me that it can't be done, and I'd be curious to know. But a bad basis is when you have eigenstates of T, and T does not commute with H prime. And so this is like a quick way. So this is a quick way to find a good basis, but I will also say it's sort of a quick way to tell whether you have a bad basis. So now let's apply it to our spin orbit problem. Apply to spin orbit case. And so now we can do now we don't have to do the brute force. Now we can skip the brute force. And now we can do clever, elegant mathematics to figure out a good basis versus a bad basis. No more brute force. No more brute force. So let's apply it now. So here's the deal. We have H prime is equal to f of r L dot S. And what we have is we have our H naught, and we have these guys. Our favorite basis is psi naught n L m sub L m sub S. Now this and so this is an eigenstate. So psi naught is an eigenstate. It's an eigenstate of H naught, right? That's how we got it. But now let's look at other operators. Let's look at the other operators, because notice that psi naught, in addition to being an eigenstate of H naught, it's also an eigenstate of this. What is the operator associated with L? Tell me. Actually, look, what is the, I'll help you out. The operator associated with N is H naught. The point I'm trying to make is every quantum number is associated with an operator. And now I want to make that connection explicit. N is associated with H naught, right? That's the quantum number. That's the quantum number which denotes the eigenvalue of H naught. L is the quantum number that denotes the eigenvalue of what? Tell me.
Angular momentum.
That's correct, but be more specific.
The L operator.
That's correct, but still not specific enough. In fact, your answer is incorrect as stated, but make it correct. You're almost there, but it's actually not yet correct, but you're right a hair's breadth from being correct. Let me just tell you a tricky thing. There are no eigenstates of L. They don't exist. That's
Is
a
it L
mathematical
squared? Oh, sorry.
Yeah, exactly. There is no eigenstates of L. They don't exist because Lx and Ly don't commute. But there are eigenstates of L squared. Yeah. So it's L squared. Good. M sub L is an index denoting the eigenvalue of what operator?
S squared?
No. M sub
Oh.
L.
L sub Z.
Yes. M sub S is a quantum number denoting an eigenvalue of what operator? Tell me. Tell me.
S of Z.
Yes, perfect. Look, these guys are the T. In the theorem, those guys are the T. That's what I want you to see, all right? Those guys are the T. So let's just take a look at, so these are like our other operators, because we have the unperturbed eigenstates also happen to be eigenstates of other operators, these third operators, in addition to H naught, these other ones, and these other ones are the T that fit the theorem. So what we got to do then is we got to ask ourselves, remember, the whole question is T and H prime equal to 0? So let's ask ourselves that. So let's first do L squared and H prime. And H prime is f of r L dot S. And so we can forget about the f of r because that's just like a scalar rate. It's just a radial function. We can pull it out. So the real question is whether L squared and L dot S equals 0. Do they? This is homework. I want you guys to actually go and figure this out. It's homework problem. But the answer is yes, it does equal 0. Okay? L squared and L dot S do commute. But now let's look at another one. LZ and L dot S. Does this equal 0? And let's look at another one, SZ and L dot S. Does this equal 0? For this to be a good basis, I would need all those commutators to equal what? Using the new theorem. For this to be a good basis, the one that you see right here in front of you, our favorite basis, for that to be a good basis, I would need all those commutators to equal what? Tell me.
0.
0.
Yes, yes. By the new theorem, I would need them all to be 0. That's what the new theorem is telling us. And so, but here's the trick. The problem is that when you go through the math, and that's part of your homework, you're going to find that these guys don't equal 0. And then that's why psi naught NL M sub L M sub S is a bad basis. It's a bad basis. Send it to the cornfield. It's a bad basis. Okay? That's a bad basis. So what we need to do is to find a good basis. So I'm going to do a trick. So now we're going to do some okay, so I hope you see that. That's because those operators didn't commute with H prime, then by the theorem, and I'm sort of running the theorem backwards. It's kind of not exactly rigorous what I'm doing, but I want you to kind of go with me on it, okay? So you can kind of see using the theorem that this is a bad basis. But now let's do it the right way. Let's go forward. And so what we can do is, let's consider a new eigenstate. Let's just find some operators. Let's find some operators that commute with our H prime. So we want to let's find some T that commutes with H prime. What is T? Well, let's do this. We already know that L squared commutes with L dot S, all right, where H prime is L dot S. So L squared is good, right? L squared is good. But we know that the LZ and the SZ are bad. Well, let's consider a new operator, J squared L dot S. And let's consider another operator, JZ L dot S. Where J is equal to L plus S. I'm adding the angular momenta. And JZ is the Z component of J. It's equal to LZ plus SZ. Okay, so let's define these new operators. And then we can calculate J squared in the usual way, L plus S dotted into L plus S. And let's calculate these commutators. And that's a homework problem. I'm not going to do it for you. I'm just going to tell you the answer. It's homework. But when you calculate it, you're going to see that these commutators equal 0. So now what we did was we did this in a really weird way. We just found some operators that commute with the perturbation. And now what I can do is, now suppose I do this. Now suppose that we take our eigenstates psi n L M sub L M sub S, and now suppose we convert to a new basis, which is psi n L, but now it's going to be J M sub J, and this is a new basis. Then the question is this a good basis? And the answer is yes, it is. where what we have to do, what we're doing is we're converting from these states, R, N, L, L, M sub L, S, M sub S, and we're converting to this basis, R, N sub L, J, M sub J, where J and M sub J are defined as follows. J squared acting on J M sub J is equal to H bar squared J times J plus 1. And you guys knew that. Let's write it all down. J M sub J. And JZ acting on J M sub J is equal to H bar M sub J, J MJ, where MJ is between plus and minus J. And what is this new state, JMJ? Well, this is just the addition of angular momentum, which we did. And you know that you can write it as, it's a sum over M sub L plus M sub S equals M sub J. I have a Klebs-Gordon coefficient, which is of L, S, J, M sub L, M sub S, M sub J, and I'm summing over all the product states. L, M sub L, S, M sub S. And this is, and I'm summing over this is where it's in the degenerate subspace of L and S. So the point I'm trying to make is that if we convert from one basis state to another basis state, then this becomes a good basis. And so this can become our new basis. And by using this theorem, we can see that this is a good basis. And so we want to convert from one basis to the other. And basically what this Klebs-Gordon, this definition of adding angular momentum just shows you that we're just rearranging the states in the degenerate subspace. And so this is an okay thing to do. And this is a new basis, and this is this basis works. This basis works for L dot S. Then we can use our perturbation formulas with this basis. Okay, and I guess that's where I'll stop, and we'll actually plug it in and calculate the perturbation next time. But what we have done is we found a good basis. Okay, folks, bye-bye.
Thank you.
Okay.
Thank you.